Good morning, students. In the last lecture, we have studied regarding the position of hydrogen in the periodic table, and now we are going to study about its compound. First, what we are going to discuss, that is hydrides. Okay, so generally hydrides are the compounds of hydrogen, the binary compounds of hydrogen with all elements. They are called as hydrides. So we can define the hydrides as hydrogen under certain conditions reacts with almost all elements to form binary compound, which is called as hydrides. So we can define here, it is a definition. So it is called as hydrides. So binary compounds of hydrogen with all elements are called as hydrides. And the general formula for this hydrides, what we can write, it is EMHN. Okay, so we can write hydride as this H2O is there, NH3 is there, NaH is there, LiH is there. These are what? These are hydrides, binary compounds. And the general formula is E is nothing but an element and H is hydrogen atom. So this is the general formula for hydrides. These hydrides are classified into three categories as we discussed in the physical classes. Okay, the outline is discussed in the physical classes. So hydrides are classified into three categories, three types. The first one is called as a ionic hydride, or it is called as saline hydride, or we can say it as a salt-like hydrides. Salt-like hydrides. So these types of hydrides, ionic hydrides, are formed by S block element. So the S block elements, the group first and second elements, they can form the hydrides which are ionic in nature. These are stoichiometric compounds. These are what? Stoichiometric means, for example, what we can write, NaH. For each sodium ion, there is a hydride ion. There is what? Hydride ion. So these are stoichiometric compound. These are stoichiometric compound and highly electropositive. These compounds are highly electropositive in nature. Secondly, the ionic hydrides, they are crystalline, non-volatile, non-conductor of electricity in solid state. Remember, in the solid state, they are non-conductor of electricity or bad conductor of electricity. Saline hydride or ionic hydride. But in the molten condition, when we melt that solid, or in the aqueous condition, they are good conductor of electricity. Why? Because compound is ionic. Whenever we dissolve it or whenever we melt it, heat it, okay, what happen? This get dissociate as Na plus and H minus. So there is ion formation in the molten state or in the aqueous phase, solution phase, and these ions are responsible for the conductivity. Ions are responsible for the conductivity. On electrolysis, okay, whenever we electrolyze, on electrolysis of ionic salt, for example, if we take sodium hydride, there is a liberation of H2 at the anode. At anode, there is a liberation of H2, and this suggests that there is a presence of hydride ion, that is H minus ion. Okay, highly reactive. These hydrides, ionic hydrides, are highly reactive with water. With water, they are highly reactive and releases hydrogen gas. This reaction also suggests the presence of hydride ion. The lighter metal hydrides, for example, LiH, then BeH2, MgH2, the lighter metal hydrides. They are covalent. The covalent character is observed. In the lighter metal hydride, that is lithium hydride, beryllium hydride, magnesium hydride, what we observed? These are ionic hydrides, but we observe the covalent character in these compounds. So covalent character is more. Stability of hydride decreases down the group in the S block. So whenever we talk about the lithium, sodium, potassium, then rubidium and caesium, okay, so the stability of these hydrides decreases down the group. So lithium forms stable hydride, sodium forms stable hydride, potassium forms stable hydride, but rubidium, caesium, they forms the stability is less for the elements. So as atomic number increases in the group, what we can say, stability of hydride decreases. So this is regarding the ionic hydrides or salt-like hydride or saline hydride. Okay, the important thing is the S block elements form this kind of hydrides, that is ionic hydrides or salt-like hydrides, stoichiometric compound, crystalline, non-volatile, non-conductor in solid state, conductor in molten state, okay, and the lighter metal hydrides are covalent in nature. Okay, the second type, what we say it as a covalent hydride, or we can say it as a molecular hydride. So here it is ions which are combined by the electrostatic force of attraction, but here they form distinct molecule. You can isolate as a molecule. So those, which are the elements which form the covalent hydride? All p block elements forms covalent type hydrides. So here is the bond between hydrogen and an element of p block, that is covalent bond. It is a sharing pair of electrons. Most important, the covalent hydrides are volatile compounds. So they are low boiling. So their boiling point is lower. So these compounds are what? Volatile in nature. Now these covalent hydrides are classified into three different categories depending upon the number of electrons present around the central atom. Okay, so the first one, what we can say it as a electron deficient hydride. So hydride in which central atom has less than 8 electrons around itself, that is incomplete octet, those are called as what? The electron deficient hydrides. And the example of this type of hydride is group 13 element hydrides. So 13 elements, one of the example I have written over here, B2H6, that is diborane. Okay, in this case, or we can say the symbol as BH3. In this case, around the boron atom, around the central atom, there are only 6 electrons. And hence it is electron deficient hydride. Okay, now this electron deficient hydrides, they have incomplete octet. There are 6 electrons around the central atom. So the central atom requires another 2 electrons to complete its octet, and hence these electron deficient covalent hydride, they are capable to accept a pair of electrons. Okay, the molecules accept pair of electrons. These molecules are capable to accept a pair of electrons, and hence they act as a Lewis acid, what we have discussed in the physical classes. So Lewis acid are the compounds or the molecules which are capable to accept a pair of electrons are called as Lewis acid, and this electron deficient covalent hydride can act as a Lewis acid. Okay, so the second type of covalent hydride, it is electron precise hydride. What it suggests that the central atom has a 8 electrons, and all the 8 electrons are bonded electrons. All electrons are bonded electrons, and this type of hydrides are formed by group 14 elements. So group 14 elements, they are capable to form these kind of hydrides. Okay, these kind of hydrides, and the example is CH4. CH4. Here, if you observe, carbon has 8 electron around itself, and all 8 electrons, they are bonded. Then third type, what we call it as a electron rich hydride. Okay, in this case, the central atom has unshared electrons around it. So unshared electron pairs, they are called as a lone pairs. The pair of electron which is not taking part in the bond formation, they are called as a unshared pair of electron, or they are called as a lone pair. And group number 15 to 17, all these elements form the electron rich type of hydrides. And the molecules are now, if we write example, that is NH3. So in case of NH3, there is a pair of electron on nitrogen which is unshared, which is called as a lone pair. Now this molecule, ammonia, what we are calling it as the hydride of nitrogen. Here nitrogen is capable to donate a pair of electron which is unshared to another molecule or an atom. Okay, so these molecules are capable to donate a pair of electron and act as a Lewis base. Okay, so what Lewis base? Lewis base are the molecules or the atoms which are capable to donate a pair of electron. That is called as a Lewis base. Now the hydrides of group 15 to 17, they are capable to donate a pair of electron, and hence what we call it as a Lewis base type of hydrides. Okay, due to high electronegativity of nitrogen, oxygen and fluorine, okay, the hydrides of nitrogen, oxygen and fluorine has a very high intermolecular hydrogen bonding, and the hydrogen bonding is due to the electronegativity of nitrogen, oxygen, fluorine, which leads to higher boiling points. Okay, which leads to high boiling point of these these molecule, that is NH3, H2 and HF, compared to the rest of family member. So this is due to the hydrogen bonding, which it shows that there is a very high difference in the boiling point of compounds or hydrides. Okay, so all elements of group 15 to 17, they are capable to form hydrides which are electron rich, but the boiling points of hydrides of nitrogen, oxygen, fluorines are higher from the rest of the member because of intermolecular hydrogen bonding. The third type of hydride, what it is called as a metallic hydride, or it is called as interstitial hydrides. Metallic hydrides, these types of hydrides are formed by D block elements. Okay. And these hydrides are non-stoichiometric and conduct heat and electricity through them. So D block elements are capable to form the non-stoichiometric metallic hydrides, or what we call it as interstitial hydrides, and these hydrides are capable to conduct heat and electricity through them. So the question is, all D block elements form the hydrides, metallic hydrides, or not? If we talk about the D block elements, uh, the Mn, okay, uh, manganese, then cobalt and iron. These three elements from 3D series, okay, 3D series. 3D series, they are not going to form any hydrides. They are not going to form the hydrides, and thus the here what we are observing, the Mn, cobalt and Fe, the 3D series, they are not going to form any hydride with hydrogen, and hence this is called as a hydride gap in the periodic table. There is a hydride gap in the periodic table. If we observe the sixth group, so these are the elements of 7th, 8th and 9th group. Okay. Here it is Fe and then cobalt. Okay, so these 7, 8 and 9, that is Mn, Fe and cobalt, they are not going to form any hydride, and that's why it is called as a hydride gap. Okay, from the sixth group only chromium forms the hydrides. Okay, sixth group, from the sixth group element only chromium, it is an element which is going to form a metallic hydride. Okay, so metallic hydrides, they are non-stoichiometric. So what it suggests that the number of hydrogen and the metal ion is not equal. It is called as non-stoichiometric, and they are capable to conduct heat and electricity. But the conductivity of metallic hydrides or interstitial hydride, it is lower than the parent metal. Okay, so actual metal, what amount of conductivity is there, it is less than that, less in case of metallic hydrides or interstitial hydrides. So here in the periodic table I will show you the where it is the what hydride gap is. Okay, so here is the, this is the 3D series, the scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. This is 3D series. This is the D block actually, scandium to zinc. Okay, and in this D block, this Mn from group 7th, iron from group 8 and cobalt from the group 9, these three elements, they are not going to form any hydride with hydrogen. Okay, and hence this is the gap in this D block, total block, okay, which is called as a hydride gap. If we talk about the group 6, the chromium, this is only capable to form the metallic hydride. Okay, the rest of group member, molybdenum and tungsten, they are not going to form any hydride. Okay, the hydrides of all other elements, for example scandium is there, yttrium, zirconium, hafnium, titanium, all they forms, or here nickel, palladium, platinum, gold, silver, zinc, copper, all they forms hydrides. These hydrides are non-stoichiometric. Okay, they are non-stoichiometric. It means it suggests that the number of hydrogen and metal atom is not equal in the compound. Okay, and why they are called as interstitial hydride? Because the small size of hydrogen, because of small size of hydrogen get enter into the empty position in the crystal lattice. So if we draw a crystal structure for that, then it goes into that empty space in the crystal. Okay, and that's why they are called as a interstitial hydride. The interstitial compound we will discuss in the PUC second year actually. Okay, what is interstitial compound and how they are going to form. Now the next thing what we are going to discuss today, that is very important, hydride of hydrogen, what we call it as a water. Okay, important hydride of oxygen, okay, or a compound of hydrogen, what we known as a water. Okay, water, all you know about its molecular formula, that is H2O. Okay, so this is the molecular formula for water. So what are the properties of water? Water is colorless, tasteless liquid. All you know about. There is no any taste for water. So आप बोल दो कि बोरवेल का टेस्ट अलग होता, वाटर का अलग टेस्ट होता है, वेल का टेस्ट अलग होता है, रिवर वाटर का टेस्ट अलग होता है. सो हमारे गांव का पानी अच्छा है, तुम्हारे गांव का खराब है, ऐसे बोलते हैं हम लोग. तो ऐसा नहीं है. एक्चुअल जो मॉलिक्यूल है, अगर ये प्योर लिक्विड स्टेट में आप लेते हो इसको, वाटर को प्योर स्टेट में, देन उसका कलर नहीं है, उसको टेस्ट भी नहीं है. ओके, कुछ टेस्ट नहीं है इसका. सो वाटर इज कलरलेस, टेस्टलेस लिक्विड. इट प्रेजेंट in the condensed form. Okay, it is present in the condensed form, in liquid state and in the solid state, both in these phases. Okay, liquid or solid phase, water is present in the condensed form. Okay, and why it is present in the condensed form? Due to hydrogen bonding, due to intermolecular hydrogen bonding. So the water molecules are always linked to each other due to the hydrogen bonds. So they are condensed. Now due to the hydrogen bonding, due to the condensed phase, the freezing point, boiling point, heat of vaporization, heat of fusion are higher than the hydrides of oxygen family. So oxygen family of all you know about. Here I will show you. This is oxygen, sulfur, selenium, tellurium and polonium. All these elements, they are capable to form hydrides of type H2E. Okay, so H2O is there, then H2S is there, H2Se is there, H2T is there. Okay, so all these elements, oxygen, sulfur, selenium, tellurium, all they forms hydrides of this type. Okay, but the boiling point, freezing point, then heat of fusion, heat of vaporization of this H2O water is very high than the rest of family member, that is hydrogen sulfide, selenium hydride, then tellurium hydride. If you observe the boiling point, freezing point, heat of vaporization, heat of fusion for all these elements, okay, this water has very high freezing point, boiling point, heat of evaporation and heat of fusion, and this is due to, what is the reason for that? This is due to hydrogen bonds. Okay, so intermolecular hydrogen bonding is responsible for this. Okay, now water has a high dielectric constant. It has very high dielectric constant, and due to which large number of ionic and polar organic compounds dissolve in it. Due to very high dielectric constant, it dissolves almost all type of compounds in it. Okay, so solubility of organic and inorganic salts is more in case of water, as it is capable to dissolve large number of compounds. Okay, all type of compounds, and that's why it is known as universal solvent. Okay, तो डाइलेक्ट्रिक कांस्टेंट बहुत ज़्यादा है. डाइलेक्ट्रिक कांस्टेंट ज़्यादा होने की वजह से ये बहुत सारे कंपाउंड्स, आयोनिक कंपाउंड्स हो, इनऑर्गेनिक, या फिर ऑर्गेनिक पोलर कंपाउंड जिनमें पॉजिटिव नेगेटिव चार्ज सेपरेशन हो सकता है, ऐसे ऑर्गेनिक कंपाउंड, ऐसे बहुत सारे कंपाउंड्स को वो डिजोल्व कर सकता है, और इसके वजह से ही उसको यूनिवर्सल सॉल्वेंट बोलते हैं हम लोग. व्हाट वी कॉल इट एज अ यूनिवर्सल सॉल्वेंट. Then the high heat of vaporization and high heat capacity. Okay, so water has very high heat of vaporization. Water has very high heat capacity, and these two properties are responsible for moderation to maintain the climate, to maintain the climate and body temperature, climatic temperature and body temperature. Okay, climate का temperature, atmospheric temperature, or body temperature in living organism. Okay, so water is responsible for the moderation to maintain the atmospheric temperature and the body temperature of living organism. And why he is responsible for that? Because of its high heat of vaporization and heat capacity. Okay, now high specific heat, high thermal conductivity, surface tension, then dipole moment. Look here, high specific heat, high thermal conductivity, surface tension, dipole moment, and dielectric constant. All these properties are high, and these properties allow the water, okay, allow the water to play a very important role in the biosphere. So, because of these properties only, that water plays very important role in the biosphere. Okay, now excellent solvent. So what we are calling it as a universal solvent. Okay, and the universal solvent. Okay, and that's why it is responsible for the transportation of ions and molecules in plants and animals. So very good solvent, and that's why it is responsible for the transportation of various ions and molecules which are the part of plant and animal metabolism. Okay, so these are the some properties of water. Okay, hope you have understood that. So today what we have discussed regarding the hydrides. Okay, hydrides of water, hydrides. Then we have discussed the types of hydride, that is ionic hydride, covalent hydride. The ionic hydrides are formed by S block elements. They are non-conductor in solid state, stoichiometric compounds, high melting points. Okay, conductor in molten state or aqueous state, release of H2O with water, and electrolysis confirm the presence of hydride ion. Lighter metal hydrides have covalent character. Okay, and the stability of hydride decreases down the group. This thing we have discussed in ionic hydrides. And then in the covalent hydrides, the covalent hydrides are formed by p block elements, volatile compounds, classified into three categories: electron deficient, electron precise, electron rich. Electron deficient hydride formed by group 13 elements, electron precise hydrides are formed by group 14 elements, and electron rich hydrides are formed by group 15, 16, and 17 elements. Okay, so electron deficients are Lewis acidic, electron rich are what, Lewis bases. This what we have discussed in the covalent hydride. Then the third type what we have discussed, that is metallic hydride. D block element form such kind of hydrides, but the hydrides are non-stoichiometric in nature. Some of them are stoichiometric also, some are non-stoichiometric. Good conductor of heat and electricity. There is a hydride gap in the D block element, what we call it as a hydride gap, and the elements are Mn, Fe and cobalt. They are not going to form any hydrides, so it is called as hydride gap. Then we discussed one of the hydride of oxygen, what we call it as a water. In that we have discussed some properties of water: tasteless, colorless liquid, condensed form. It is present in the condensed form in the solid and liquid phase. Then high freezing point, high heat of vaporization, heat of fusion due to the hydrogen bonding. It has high dielectric constant, hence called that as universal solvent. High heat of vaporization and heat capacity. Okay, allow the water to maintain the body temperature and climatic temperature. High specific heat, thermal conductivity, surface tension, dipole moment, dielectric constant allow the water to play an important role in the biosphere. Very good solvent, very excellent solvent, universal solvent, and hence responsible for the transportation of ions and molecules in the plants and animal metabolism. So this is regarding the today's lecture. Thank you. Remaining part we will discuss in the next lecture.